Hello everybody, I'm Grace Nye, and I'm a biochemistry major, so today I will be presenting to you about the angular momentum of electrons. Okay, so first we're going to take a look at one of the most classic and simplest models for electrons in the atom, and this is called the Bohr model. And in this model, you see the electrons orbit around the nucleus like so, taking a circular path. So these electrons, all of them have a linear velocity, and remember, velocity is a vector quantity, so it has both direction and magnitude. So even if this electron is flying around the nucleus with a constant speed, because the direction is always changing, we say that the linear velocity is always changing. And this is due to a centripetal force, which is pulling the electron towards the center. And that is the electrostatic attraction between the protons, which are positively charged in the nucleus here, and the negatively charged electrons out here, flying around. These electrons also have angular momentum. Remember, angular momentum, as we studied it, in a closed system, it's always conserved. So, what's really important to know about atoms is that while they remain undisturbed, they all have constant angular momentum and constant energy. But if there is some external force acting on it, some net torque, this can cause a change in the angular momentum or the velocity, either angular or linear. Now, as you get a little bit further into studying this, it gets a lot more complicated, so we get into some quantum physics here. And so there are 4 quantum numbers which are used to describe the state of the electrons in their orbitals. So the first one of these is called the principal quantum number n, and this one is just used to describe the size or the energy level of the orbital. So as you can see here, as the value of n increases, the size of the radius increases, and so does the energy of the electrons. The next number that we're going to talk about is the quantum number L, and this one is just used to describe the magnitude of the angular momentum. Magnitude, not direction. Magnitude. So as the magnitude of this angular momentum changes, this changes the shape of the electron orbital. So for a value of L, which is equal to 0, as we would say, we have an orbital which we call an s orbital. And this just looks like a simple sphere, as shown here. So it's like a big circular spherical bubble of electrons around the nucleus. When L equals 1, so the angular momentum the value of it has changed, then we have what we call a p orbital, and this looks like this. It's like a dumbbell. And this is actually super interesting because it also resembles wave functions, which we've also studied. So there's a positive side and then a negative side on either side of this axis here, which passes through the nucleus, and there's a node at the center where there's no electrons at all. Interesting. As the value of n continues to increase, so this angular momentum continues to increase, we get d orbitals and then some f orbitals. And as you can see, they're just getting more and more complex as this angular momentum is growing. Then the third quantum number is m sub L, or the magnetic quantum number. And this is just, we can think of it as loosely referring to the direction of the angular momentum. So the last quantum number, L, was the magnitude of angular momentum. This one is the direction. So for your p orbitals here, there are 3 types. There are 3 different p orbitals. There's one in the x-axis, y, and the z-axis. And so this number just tells you which direction it's pointing, which dimension it's in. Finally, the last quantum number is m sub s, and this one describes electron spin. So as the electrons are flying around the nucleus, they also have some rotation occurring around their own axis. So kind of think about like the Earth as it's revolving around the sun. It also spins on its own axis to give us days and nights. So electrons do the same thing. They spin along their own axis. So this quantum number, m sub s, just describes the angular momentum of that electron's rotation. They always have the same magnitude, 1/2, but they can have either a positive or a negative direction, so spinning up or down. That's one way to think of it. Now, according to the Pauli exclusion principle, we know that every electron must have a unique set of quantum numbers. No two electrons can have the exact same quantum numbers. And basically, this just means that in every orbital, only one electron can spin up and one can spin down. And so there's never any more than 2 electrons per orbital, one spinning up and one spinning down. And finally, I just wanted to close with just a little reminder that all of this is an extremely simplified version of what's really going on. We know that these orbitals, they're not actually like circular paths or uniform paths taken by the electrons. It's more like an electron cloud. So these orbitals are like mathematical predictions of where the electron density is probably distributed. These electrons are really like flying around like crazy in there. And there's all sorts of math, really complicated math that goes into figuring out exactly where it might be at any given point in time. Okay, so these are all my references, and thank you so much for watching.